This is problem 49, and it is a homework problem. A disabled tanker leaks kerosene, which has an index of refraction of 1.20, into the Persian Gulf, creating a large slick on top of the water. The water has an index of refraction of 1.30. Part A reads, if you are looking straight down from an airplane at a region of the slick where its thickness is 460 nanometers, which wavelengths of visible light do you see reflected? Now, interestingly enough, there is a very similar problem in the Halliday and Resnick physics textbook. And that problem gives you some additional information, and it says the sun is overhead, which means the light would be shining down perpendicular to the surface, which again is not the way I've drawn it because everything would be on top of each other if I drew it that way. But you can assume that the light is perpendicular to the surface when you solve this problem. So your path length difference would be twice 460 nanometers. Okay, they also, in the Halliday and Resnick physics textbook, asked the question this way: for which wavelengths is the reflection the brightest due to constructive interference? So that is what you are looking for with part A. You should be able to do that on your own, but part B is a little trickier, so we're going to look at that one now. So part B reads, if you are scuba diving directly underneath the same region, which is right underneath the oil slick, so I don't know why you would want to do that, but if you were, which wavelengths of light do you see transmitted? Or in Halliday and Resnick, the question asks, for which wavelengths is the transmitted intensity the strongest? And then you may wonder, should you be giving the wavelength in air or in water? So the path length difference here takes place in oil, but you wouldn't give me the path length difference in oil because the light comes back out into the air, and that's what you should be giving me. Here, however, you do have to ask that question because you are scuba diving in the water. So it makes sense to give the wavelength in the water, which is actually what the answer is in the back of the textbook. So if you're checking your answer in the spiral physics textbook, that wavelength is the wavelength of the light in water. So that's what you should be giving me. However, in the Halliday and Resnick textbook, for the same question, the answer that they give is the wavelength in air, which also makes sense because if you want to compare it to the visible spectrum, you know the wavelengths for the visible spectrum in air, so it makes sense to give all the wavelengths in air. So either one of them would be acceptable if you were just solving this problem on your own, but because you're going to turn it in for homework, I want you to give me the wavelength in water. Okay, so now the reason that we're doing this together is because, as we talked about in one of the previous problems, the light's going to shine down. Some of the light is going to go straight through the oil and end up in the water, but some of it is going to be reflected at this surface, and some of it is going to be reflected at that surface, which gives us what we have up here. But because we're in the water, we're going to look at the light which goes straight down to the water. But I have a problem if I just look at this light wave because there's nothing for the light to interfere with. So I have to keep going until I get another light wave which is coming down into the water. So I can ignore what's going on up here because that's all in the air. It's not going to change anything for this problem. So at this surface, part of the wave is reflected, and then at this surface, part of the wave is reflected again and goes down into the water. Now we could look at all these other light waves that make it down into the water, but we're looking, as the Halliday and Resnick textbook says, for the wavelengths where the transmitted intensity is the strongest. So the intensity is going to be the greatest for these two waves because every time it reflects, you lose some intensity. So we can ignore the light waves that you would get if you keep going and look at all the reflections and transmissions because these ones are not as intense as the first two. So we're just going to look at the first two that make it into the water there. And there'd be no phase shift for this wave here because it wasn't reflected at all, and you only get a phase shift if the light is reflected. I put the index of refraction down here, but I forgot to do it down here. So this is n is equal to 1 for air, 1.20 for oil, and 1.30 for water. So remember, from our equation sheet, if the reflection is off a lower index of refraction, there's no phase shift. If it's off a higher index of refraction, there is a phase shift. So we're reflecting off of air here. We're in oil. That's off a lower index of refraction. And so there's no phase shift here. And for this one, we're reflecting off of oil, so there is a phase shift. So we have a phase shift of pi here. We have no phase shift here, so when this wave comes out, it's going to have a phase shift of pi because there was a phase shift of pi here and then no phase shift there, so we still have a phase shift of pi. And this one, there's no phase shift. So overall, there is a phase shift. So are we looking for constructive interference or destructive interference? If you're looking for what you see or when the transmitted intensity is the strongest, that would be constructive interference. So constructive interference, where the two waves are out of phase, would be 2d is equal to m plus 1/2 times the wavelength in the material. Remember, this is the material in which the path length difference is happening, which would be oil. So let's just put that in there. This would be for oil. I don't want the wavelength. I don't want the answer to be the wavelength for oil. So we either need to find the wavelength in air or the wavelength in water. And we're going to find the wavelength in water. In this case, so we get to use this equation twice, right? Because I have the wavelength in oil here. I can take this and from this equation find the wavelength in air, but I don't want the wavelength in air. I want the wavelength in water. So actually this equation came from another equation which says wavelength 1 over wavelength 2 is equal to index of refraction 2 divided by index of refraction 1. So you could just use this equation twice, and I gave you this equation instead because I think this is the only problem in which this would be useful to us. But either from this or from using this equation twice, we should find that the wavelength in oil, so that means 1 is oil, is equal to, bring this over to the other side, so that's wavelength water, times n water divided by n oil. Let's go ahead and put that in our equation here. So now I have 2d is equal to m plus 1/2. Wavelength oil becomes wavelength water, which is the answer you should be giving me, times n water divided by n oil. N water is 1.30 and oil is 1.20. So I'm going to stop here and you can finish this for homework.